In this lesson, we're going to be taking a look at how to solve polynomial equations algebraically. And so it's all going to be different methods that we can use for solving it without having to make a graph. Although for each one, I will also show the graph just as a way to kind of see what it attaches to. But we won't actually have to make a graph for any of these methods. All right, so for this first one, we have 8 equals x cubed. Hopefully, you can actually even just look at that and know what x is. But if not, we can yet solve it. So in order to undo the cubed on the right-hand side, we would need to apply a cube root to both sides. And so I'm going to do the cube root of 8 on the left, and I'm going to do the cube root of x cubed on the right. So then on the left side, I do the cube root of 8, which actually calculates to just be 2. And on the right side, I have x to the, well, remember rational exponents means that it's x to the 3 over 3. 3 over 3 equals 1. And so that just equals x to the power of 1, which is just x. That's why the cube root undoes cubing. Now, what that really told us there is that when the x value was 2, we got the y value of 8. Notice you can see that on the graph where when y is 8, I'm hitting the x coordinate of 2. And so that's really what it's kind of showing happening there, right? Where a is playing the role of our y value. All right, on to our next problem. Now the numbers aren't going to be quite so pretty. So we have x to the 4th equals 5. Well, I want to undo the 4th power so that I can just have x left behind. So I'm going to want to do the 4th root of both sides. So 4th root of x to the 4th, and I'm going to do the 4th root of 5. So on the left side, notice that the 4th root and the exponent of 4 cancel each other out so that all you're left with is x. If you want to start by writing it as x to the 4 over 4 and then simplifying it just to make it super clear, you're welcome to do so. But then on the right side, I have to do the 4th root of 5. And your calculator probably does not have a 4th root button on it. And if that's the case, then you can just rewrite this then as x to the power of, 5 to the power of 1/4. That gives you then something you can calculate. And so here, x just equals about 1.5 if we round it to the nearest hundredth. So let's go ahead and make that an approximately equal there. There we go. That way we show we rounded it. Now, if I again wanted to connect this back to the graph, what am I going to see? Well, if I take a look at the graph, you'll notice there that I'm hitting that point right over here. That's the point where y was 5 and x was about 1.5. But you'll notice that there's a little bit of an issue with our graph because if I look over to the left from there, I see there's actually another point where I actually hit a y value of 5. That is also a solution. How do I need to account for it? Well, there's actually another additional little rule here where anytime you take the 4th root of both sides of an equation, you have to account for both the positive and the negative versions of your answer. So actually, x here would equal about 1.5 and negative 1.5. And that's going to be true every time you take the 4th root. And in fact, it's going to be true anytime you take any even root. The reason is because anytime you have an even exponent on something, your graph ends up looking kind of like this, where your graph is going up equally on both the left and the right. Now, of course, there can be variations for that, but it does mean that your graph is going up on both sides or going down on both sides too. Well, if we were looking at an odd one, so like x to the power of 3, remember that looks like this? Notice it doesn't double back on itself. And therefore, we don't have to worry about the two solutions in that case. It's only when it's even. Now remember that going forward. Let's go ahead and take a look at another practice problem here. What if we were doing x to the power of 4 equals negative 5? Well, we'd solve it much the same way, right? And we'd end up getting down to where we'd have to figure out what the 4th root of negative 5 is. And so into your calculator then, you would type in negative 5 to the power of 1/4. And something interesting here can happen Because if your calculator here tells you that it's negative 1.5, it did what you told it to, but it's wrong. Because when you actually type something like this into your calculator, you're going to be typing in negative 5 to the power of parentheses 1/4, because you're remembering the parentheses around your exponent, right? But what it's actually seeing when you type something like this in is it's not actually seeing negative 5. It's actually seeing negative 1 times 5 when you do that. And because of that, it then goes and does the exponential part before it does the multiplication. And so you may well find that on your calculator, when you go and type in something like this, you'd actually have to take your negative 5 and put it also in parentheses in order to show that the negative 5 is being raised to the power of 1/4. And if you do that and do it correctly, your calculator is actually going to give you an error. And it can display the error in lots of different ways. Some calculators just display an E on them to represent error, but it actually is not possible. I'm actually going to say the answer is DNE, which is short for does not exist, because there actually is no solution. And actually, let's go back to our graph to see why that is. Because if I take a look at my graph here, I'm looking to see where does my graph hit a y value of negative 5. It never does. And hence, we wouldn't expect a solution for that reason. And so we have a couple rules that we saw here when we're solving with radicals. When you end up having to take an even root of both sides, you have to account for both the positive and the negative solutions. So we'll have both positives and negatives in each of those. And remember that even roots of negative numbers are undefined. Now, these are both very specific to even roots. Odd roots do not have this problem, because remember, like if you think of a cubic graph, notice that it's not doubling back on itself. It includes all of the different values out there. And so because of that, you're not going to run into some of the same issues that you do when dealing with evens. Go ahead and write this down to your notes, pause if you need to, and then proceed with the video. Now that we have those basic ideas down, we can now tackle a much more complicated question like this, and we can actually solve it out. So then, remember back to what we did with solving absolute value equations, where you wanted to get the absolute value by itself first. This is going to be the same idea. Just in this case, you want to get the stuff that's to the power of 6 by itself first. So notice that means I got to get rid of the 2, and I got to get rid of the negative 3 before I can do anything else. Well, in order to do that, I want to get rid of the minus 3 first, because we always get rid of the addition subtraction first. So I'm going to go ahead and add 3 to both sides of my equation here. And then I can look to get rid of the 2. Since the 2 is just written out front of the parentheses, it's multiplying it. And so to get rid of it, I will divide both sides by that 2. So we've now successfully gotten the x minus 4 to the power of 6 by itself. I now need to get rid of that exponent. And I get rid of it by taking the 6th root of both sides. And so that means I'm going to end up having to do 5 to the power of 1/6, which gives me about 1.31. Now I'm going to go ahead and keep that whole decimal showing on my calculator here at the moment. And that equals x minus 4, right? But remember that we just took an even root of both sides. And therefore, just like when we solve absolute value, we also must account for the negative solution as well. So I'm going to also have to do one over here that's negative 1.31 equal to x minus 4. All right, now I can go ahead and finish solving them out. I'm going to go ahead and add 4 to both sides. And when I do so, I end up with answers of about 5.31. And yes, double check that that's rounded correctly at the very end. That's why you want to use the whole decimal at this point. And your other one should be about 2.69 for x. And so those would be our 2 rounded solutions that we would provide for this problem. And once again, just to be able to see where that's showing up on the graph, if I made a graph of the same thing, so I'm graphing this over here, and I look to see where does that actually hit a value of 7, So a y value of 7, I can see those two numbers pop up right there. It's just that if I was relying on the graph to find those values, I would have had a tough time knowing that that's exactly what they were at. And so this is the big advantage of being able to solve them algebraically, because we can now go ahead and find some values that we would not have been able to precisely find otherwise. Now there is another form that you're going to see of this type of equation though, another polynomial form, which is factored form here. And this method that we're going to take a look at for this type of problem works as long as the whole factored form is set equal to 0. And being equal to 0 is so important because of the zero product property, where if I can make this set of parentheses equal 0, then I know that 0 times anything else will equal 0. And because of that, since everything is being multiplied there on that left-hand side, I can just figure out what the solutions are by making each of those different parentheses, each of the factors that is, equal to 0 individually. So let's take a look at that first one. X plus 4 equals 0. Well, what plus 4 equals 0? You hopefully can just know off the top of your head, but if not, you could always actually write out a little equation and solve it. Because if I subtract 4 from both sides here, notice that tells me that x would equal negative 4. And therefore, if x equals negative 4, then the whole thing will equal 0. But of course, that's not the only option, right? Because what if I made the second set of parentheses equal 0? What would I have to plug in there? Looks like negative 3, because negative 3 plus 3 is 0. And then I just keep going down the parentheses in the exact same way, looking to figure out what can I plug in for x in each parenthesis that makes it equal 0. And then that ends up being my solutions. And so in this particular case, there are 4 different solutions, which we've seen come up as the zeros of our graph. And so really what we're doing is just figuring out where those points are, those x-intercepts on our graph this way. Now, the last type of scenario that you're going to see is something that looks like this. If I could factor it, this would be very easy, because I could just do what I did on the last problem, is set each of the factors equal to 0. But it's not factored. And this one's pretty tricky to factor. We haven't seen how we could factor such a thing as this ourselves. And so instead, if you are faced with a problem like this that you need to solve, and you have no other way of doing it, there is always at least one way, and that is to graph it. And I will often use the Desmos graphing calculator for this. I think it's a great resource for it, but you can use any old graphing calculator. And then once you've made the graph, we're looking to see where does our graph hit 0. And so I can see that it crosses my x-axis at 3 different points. Notice it's cubic, hence I would expect up to 3 zeros. And so I would end up here with x equaling negative 2, 1, and 3. And that's all I'd have to do is look at my graph to find that out. The trick is, of course, is that this only works as long as those are nice, pretty numbers. Well, when we start getting a combination of ones that aren't nicely factored and they don't work out to nice, pretty numbers, we'll talk later about how to deal with some of those situations. But for now, these methods should take care of you.